Okay, hello everyone. Thanks for joining me in this session. This is the second session for the MDI workshops, and this one about the vibration analysis. The first session, it was about the data collection and how you collect vibration data. And this one, we're gonna go quickly through the different vibration analysis faults with few samples or case studies or cases, how it looks like on the vibration spectrum. Hopefully this will not be a long session. We'll go through many faults, and the whole session will be recorded and uploaded to the YouTube. I tried to send the link for many participants or many guys who registered on the to attend the workshop. I don't know why it's not received. Maybe because there was too many and I put all of them in one email, and that's why it's not received. That could be the reason. I'm not sure. That's why I put the Zoom link to attend the session on the LinkedIn, but it seems that not too many people attend. Yeah, start more coming now. I think this will happen through time. So we have, I think, about 9 or 10 guys joining now. I believe there will be more joining during the session. And okay, let's start. The first fault, before I start, everyone, if you could please give me a thumbs up if you can hear me well, loud, clear, with no echo, and you can see my shared screen. Excellent. Thanks, Martin. Thanks, Mohammed. Perfect. Let me make my phone silent, and then we can start. Excellent. So the first fault we're going to talk about is the imbalance, or the what we call 1x fault. We have few types of the imbalance. The first one is the static imbalance, and for all type of imbalance, the spectrum will show 1x vibration. And if you have static imbalance, if you have dynamic imbalance, if you have couple imbalance, all the time you'll see high 1x vibration with almost sinusoidal sine wave in your time wave form. And also when you see high unbalance vibration on any of machines, like let's say if you have high imbalance on one of the fans, blowers, pumps, it's pretty easy to see few small amplitude harmonics as a result of, let's say, looseness. And the looseness will come as a result of the high vibration caused by imbalance. In static imbalance, you will see if you have, this is your rotor or your shaft, you will see the two horizontal vibration will be in phase and the two vertical vibration will be in phase as indication of static imbalance. For the couple imbalance, you will see high 1x as well, but the phase will be out of phase across the shaft or across your impeller, two bearings, if the impeller, let's say, center hung. So across the two bearings, you will see the phase reading out of phase horizontally and vertically. And this what we call couple imbalance. Dynamic imbalance will be very similar. Also will show you high 1x vibration, and it will be out of phase across the shaft or across the two bearing or between the two bearing before and after your impeller. And this also would be indication of dynamic or couple imbalance. And in this case, you will need to do two plane balancing. For couple, you will need to do two plane balancing. For static, it can be done by single plane balancing only. And in the three different imbalance faults, you'll see high 1x vibration and you will see sinusoidal sine wave. The relationship between vibration between horizontal and vertical, vibration horizontal could be double or maximum triple the vertical to say we have imbalance. If it's 4 times, 5 times the vibration in horizontal than the vertical, so this could be indication of structure looseness, which as a result of high flexibility in the structure or lower stiffness, which need to be adjusted by stiffened supports or do some modification for the structure itself. Imbalance is the force and the measured vibration is the response, and this response or this forcing frequency can affect your structure and cause this structure looseness. And if you reduce the vibration of the forcing frequency, which is the imbalance, this definitely will reduce the effect of the forcing frequency on my structure, and it will reduce the vibration caused or or the vibration causing the structure looseness as well. So by balancing the machine, this could be a solving or it could be a solution to solve the structure looseness problems. This is how the imbalance will look like in the vibration spectrum. You'll see high 1x vibration and with almost sinusoidal sine wave. This is again how the imbalance will look like with high 1x vibration, high 1x vibration. The eccentric rotor fault analysis. The eccentric rotor happens when the center of rotation is offset from the center of geometry. And this can happen in volley, in gear, bearing motor, etc. And the main and high amplitude vibration can be seen at the running speed 1x vibration. So it's similar to the imbalance. And the phase difference between horizontal and vertical will be mostly in phase. If you try to balance a rotor have eccentricity, the vibration could decrease in one of the radial direction and will increase on the other one. So normally you have eccentric rotor or eccentric pulleys. You will see it in the belt-driven machines. For bent shaft fault analysis, you will see also high 1x vibration, mostly at the axial direction. And the axial phase reading will be out of phase, like if this is your rotor and you measure the axial vibration along the rotor, it will be out of phase. And you need to remember the orientation of the sensor is very important. You might see 2x on the vibration spectrum if the bend was near to the machine coupling, and 1x will be higher if the bend near to the shaft center. For structural looseness, you will see high 1x vibration as well, but the difference between structural looseness and the imbalance that you will see vibration in horizontal direction will be much higher than the vertical direction because of the stiffness difference, but it will also give you high 1x vibration. Also, soft foot is one of the reasons which can cause high 1x vibration. And one of the good solution for that you can do something called soft foot dynamic testing. Like while the machine is running, you can lose one of the hold down bolts at a time, like once, like one hold down bolt at a time, lose it and then retighten this bolt again. While you're measuring the vibration live, like you will put your vibration sensor on the direction with the highest vibration. Let's say horizontal vibration is the highest. You will put your sensor horizontally on the drive end, for example, of the motor, and then you will lose one of the hold down bolts and then retighten this one again. Go to the next one, lose it, retighten again. Go to the third one, lose it, retighten again. And then go to the fourth one, lose it, and then retighten this one again. Once you do this, you will notice some change in vibration in one of the motor feeds. And based on that, you will see drop in the vibration level, and this foot or this feet need to be shimmed because it have soft foot. I have a good video in the MCS YouTube channel showing live test for one of the motors. It's motor coupled with a pump. And when we lose one of the hold down bolts, vibration drop from 12 to 1.9. We're just losing one bolt. As you can see, this one as well, the vibration was 16. We lose one of the hold down bolts, drop from 16 to 1.35. From 16 to 1.35. This is because of the soft foot. And as you can see in the vibration spectrum, high 1x vibration. For the misalignment, we have two types. We have the angular misalignment and we have the parallel or the offset misalignment. The angular misalignment should see elevated vibration at the running speed component 1x with the second harmonic 2x on the axial direction. Mostly 1x amplitude is higher than 2x. Do not get confused between the angular and the offset or the parallel. Remember this. The A as a letter come before the B. So if A first, so the 1x first, and B second, so the 2x will be the highest. So with angular, you'll see higher 1x. With the parallel, you'll see higher 2x vibration. Normally, it's a combination between them, between the angular and the offset or the parallel misalignment. This is what you're going to see on any asset when you do the data collection and the analysis. You can see 1x and 2x with lower 3x amplitude on the radial direction. Phase measurement across the coupling will be out of phase 180 on the axial direction and will be in phase on the radial. Severe angular misalignment can cause 1x with harmonics similar to looseness, but with no noise floor. The parallel misalignment, you will see elevated vibration at the running speed component 1x with the second harmonic 2x on the radial direction. And mostly the 2x amplitude is higher than the 1x. And you can see 1x and 2x with lower 3x amplitude on the radial direction. The phase measurement across the coupling will be out of phase about 180 degree on the radial direction. Misalignment will be caused by improper alignment or because of the missing thermal growth calculation from your calculation. And when we do the alignment, also you have pipe strain, and this can be one of the causes for the misalignment. As you can see here, measuring the phase in the vertical direction, and we measure the phase also in horizontal direction across the coupling, this definitely will be very helpful. And also we measure the phase in the axial direction. If it's out of phase horizontally and vertically, mostly you have parallel misalignment. And if it's out of phase on the axial direction, this will be angular misalignment. And please be careful about the sensor orientation. As you can see in looseness, you'll see 1x and harmonics with high noise floor, but with misalignment, you'll see 1x and harmonics with no noise floor if you have severe misalignment. We have various vibration response to misalignment depend on the coupling type, but this is one of the good things. If you have your vibration, if you have a jaw coupling, you might see 1x and 3x, and you can see 3x and 6x are the dominant vibration peaks or components. If you have gear coupling, you will see higher 1x vibration on the radial direction. Also, you can see 1 and 2, and the 4x would be higher. This is after too many experiments and many testing with different coupling types on motor and pump. We came to this end that we have, this is the different vibration pattern in case of misalignment with different coupling types. It's not necessary to see this exactly the same, but could be a good guide for you if you do analysis and then you find different patterns and you don't know what this pattern is caused by. And you're trying to link this to any of the forcing frequencies and you can't. So it could be misalignment because of the coupling type. So keep this in your mind. This is a good guide. For the metallic grid coupling, you will see high 1x vibration, or you might see high 4x vibration. For the flexible disk type coupling, you might see elevated vibration at 6x or 2 and 4x. For rubber coupling, you'll see 1x, 2x, and this is the most common pattern for the misalignment. For cooked bearing, you will see 1, 2, and 3x, and cooked bearing looks very similar to misalignment. Will be seen in the spectrum as elevated vibration at 1x, second, third harmonic. Cooked bearing will cause twisting motion, and they will cause phase shift 180 degree on the axial direction, top to the bottom and left to the right around the bearing face. For vertical offset misalignment, this is how the alignment looks like and this is how we can shim it. For horizontal offset, this is how it looks like. And for the angular misalignment, this is how it looks like. And if you want to shim it, this will be the way. And this is the angular misalignment for horizontal. And this is how it can be adjusted if you look from the top view. This is how the misalignment will look like. You will see 1x and 2x, and also you will see W, or we call it M shape. Like this is the M shape on the vibration time waveform or time domain. You can see 1x, 2x, 1x, 2x, 1x, and 3x, 1, 2, 3x. This is all patterns of how the misalignment will look like. For pump and compressor fault analysis, normally you will see the vane passing frequency. The vane passing frequency is the number of vanes multiplied by the running speed. You can see side bands around the vane passing frequency, and you can see the second harmonic. And this could be indication of flow turbulence problems, step clearance problem, uneven clearance between the impeller and the volute. This all can cause this. And also seeing the vane passing frequency doesn't necessarily mean that you have a certain fault. Like if you see the vane passing frequency, this could be an indication. This could be just the characteristic frequency appears on the pump or the compressor or the fan. So seeing the vane passing frequency doesn't mean that we have a fault. But if the amplitude increased, if the harmonics, if the side bands, so definitely you have something. We have two main faults, which is flow faults happen on bumps, which is the cavitation and turbulence. Cavitation usually happen when the suction pressure or the intake is restricted, and you have the net positive suction head is below the liquid vaporization pressure, and the liquid vaporize when it coming over the impeller, and the high noise will be generated, and you will see high amplitude humps or high noise floor around the vein passing frequency on the right side from the spectrum, and also you will see random impacts on the time waveform, and you can hear the voice which voice similar to that one which you're gonna hear when you have the cavitation, and and the suction line will have very low pressure if you have any something restricting the suction, so the pump will be like it's pulling more air. The turbulence is the second, or what we call circulation, happen when you got high back pressure, low flow, low discharge angle. You have obstruction on the discharge line. You have sharp elbows on the discharge line. And this causes humps or high noise floor at the subharmonic or at the low range left side around the 1x vibration. So you can see this noise as a subsynchronous or below the 1x. This is how the cavitation will look like around the vein pass frequency. This is how the cavitation will look like. This is also similar shape for cavitation. For the next fault, which is the bearing fault analysis. Bearing fault analysis is one of the very common faults, and you have different stages. Like the stage 1 or the first early stage for the bearing fault is stage 1. You have subsurface damage only, and friction and the minor impacts, very high frequency vibration, greater than 20,000 hertz, slight noise and no high temperature, very short duration impact in your time waveform. As you can see here in the vibration spectrum, you'll see very high, like you see high noise floor at the very high frequency between 5,000 to 40,000 hertz. This will be stage 1. There is no a real defect can be seen, and if you take a decision to replace the bearing at this stage, that should not be the right decision, because when you take the bearing out, you almost see nothing. In stage 2, also you still have subsurface damage, only friction and the minor impact, very high frequency vibration start to increase, vibration significant enough to excite structure, bearing, and sensor envelope, demodulation, and sensor envelope. The modulation spectrum will show defect sign on the spectrum. Velocity spectrum still will not show any defect. So between 1,000 to 5,000 hertz, you will start to see some peaks, could be indication of early stage bearing fault. Also at stage number 2, we not do anything. We just like monitor. We keep an eye on the bearing and see for any further changes or deterioration in the future or in the next survey. Yes, in stage 3, you'll have more significant damage. And normally when I do my call, I do it in early stage 3. Bearing could fail in many ways for many reasons. Very high frequency increase in the amplitude between 1,000 hertz to 5,000. You'll start to see let's say the outer race defective frequency with harmonics and at the velocity spectrum. So at this stage, you need to take your decision by replacing the bearing. Stage 4, you might see more harmonics, more side bands, and all those frequencies on the demodulation, enveloping, big view will disappear, and you'll see high noise. That's it. And all these frequencies or all these bearing frequencies will be masked by the high noise. At the last stage, you will see the running speed with harmonics, bearing already failed, with high noise floor, and in this case, you don't even need a vibration measurement to know that you have a bearing fault. So mostly we change the bearing on stage 3 to be sure that when you take the bearing out, you will see a damage. For this one, as you can see here, this is inner race bearing defect. This is the velocity spectrum. You can see the inner race, and it's lining up with the inner race defective frequency, which is already calculated for this bearing. As you know, for every bearing, you have 4 fault frequency: inner race, outer race, cage, and rolling element. If you have the bearing number and if you have the running speed, you will go in the software and you will enter the running speed for this shaft, which have the bearing attached to, and you will put the bearing number, and then the software will automatically calculate for forcing frequencies, and it will be added to the software as an input frequency or input fault frequency, which you can view when you're doing the analysis. That would make it easier for you when you choose the bearing type, or when you want to view the fault frequencies, and it can be lined up and matching any of the non-synchronous frequencies. As we know that the bearing fault are non-synchronous or non-harmonic vibration. So when you see, let's say, the running speed with harmonics, and then you will start to see non-synchronous vibration with harmonics, with sidebands, you start to have some suspicions that this could be a bearing fault. Then you will feed, if you didn't do already, you will feed the software with the bearing number and with the running speed of the machine. And this is supposed to be happen before you start to do the analysis. That should be the best practice to make the analysis more accurate and efficient. And once this happen, you will start to view the bearing faults, and it will match those non-synchronous peak. When they match it, you will be sure that, okay, this non-synchronous, which matching one of the bearing faults, so this is a bearing defect. So as you can see here, we see this non-harmonic component and with few harmonics, and when we line it up with the inner race bearing defective frequency, it matching them. When we look for the big view spectrum, you will see also the non-synchronous peaks with harmonics with sideband at the running speed, and this was a good indication of bearing fault. This is stage 3, and please be careful, even on the stage 3, there is early stage 3 and late stage 3. Like you see here, the amplitude is 2.1 Gs, and the vibration amplitude is 0.7 millimeter per second. If you wait a little bit, you will see this amplitude start to grow and increase. So every stage, there is start and the end of the stage. The time the bearing would take at this stage is not predictable. Like you might be in stage 3 for 4, 3, 5 months. You might be in stage 2 for 4, 3, 5 months for 1 year. Okay. And you might be for 6 months. That's why we need to do a routine data collection. And that's why when we start to see that the bearing in stage 2 or stage 3, and we'll start to see some changes, we can reduce the frequency of the data collection to keep an eye. That's why we put a recommendation is to monitor at lower frequency for this bearing, especially if the machine is critical, to be able to capture any changes or any deterioration between every 2 measurements. So as you can see here, this is the fault frequency, which is 60.27 with harmonics, and you see the side bands. When we open the bearing, we see some dents and we see some defects appear, and it was false patterning problem. As you can see in this one as well, this is the fault frequency with many harmonics, and the amplitude, as you can see, is magnified or increased in the high frequency range, because in the high frequency range, the vibration will be magnified as the end of the linear range of your sensor. And you can see here, this is the defective frequency started from here and end to here. This is in the velocity spectrum. And in the big view, you will see also the defective frequency with harmonics. This is outer race bearing defect, and we see side bands. Normally, the outer race is fixed, so you should not see side band. But here in this problem, we found that this was a combination of 2 things. We have outer race defect, and the bearing also was skidding, was rotating in the bearing housing. And this could be the reason why we see the side bands for the bearing fault frequency. Normally, you see the bearing fault frequency with side bands for the inner race, because the inner race is rotating, and we should not see that when we have the outer race defect frequency. But in this case, we see it because we found that the bearing is already skidding because of the high clearance inside the housing. As you can see also, this is inner race defective frequency. It can appear on the velocity spectrum and also in the demodulation spectrum. And you can see the sudden change on the vibration level. And this is also very important. As I mentioned, you cannot predict how long the fault will be at every stage. As you can see here, this is outer race defective frequency with harmonics, and we can see impacts on the time waveform. Also, this is the outer race defective frequency with harmonics, and this is floated outer bearing, because you have one of the faults called floating when the bearing is not insulated, and you have some electric discharge going through the shaft to the bearing, to the rolling element, to the inner and the outer race, causing this floated outer bearing race defect. As you can see here, this is inner race bearing defect with harmonics and side bands, and you can see amplitude modulation in the time wave form. The next fault we have here is the belt fault, and when you have worn, loose, and mismatched belt are considered the main problem in the rotating machine. Belt defect frequency are of the subharmonic type, and belt drive problem, which include shaft misalignment, you have body misalignment, you have belt wear and resonance, belt are too tight or too loose, body eccentricity and bend shafts can be relatively straightforward to detect, but can be far more difficult to specifically diagnose and correct. You can calculate the belt rating frequency from this equation. And as you can see, you will see the running speed of the motor with harmonics, the running speed of the blower with harmonics, and you will see a subsynchronous vibration with harmonics. And mostly this is the belt frequency. It starts as subsynchronous and with harmonics. We have, if you have vertically angled misalignment, horizontally misalignment, parallel misalignment, this all can cause belt problems or belt rated faults. And you will see high 1x vibration, like mostly you will see if you have motor and blower, and the motor have its own running speed and the blower has its own running speed, and both are different because we have different poly sizes. When you measure the vibration at the motor side, mostly you should see the 1x motor is higher at the motor side, and the 1x fan should be higher at the fan side. But in case of the poly misalignment, you will see the high 1x of the fan on the motor side, like the vibration of 1x or the running speed of the fan will be higher on the motor, and the running speed of the motor will be higher on the fan. It will be like vice versa. It will be swapped. And this is a very good indication of Bolli's misalignment. It can do that. Also, we can calculate the speed from the diameters, like S1 D1 equal S2 D2. D1 is the diameter of like the smaller pulley, and D2 is the diameter of the bigger pulley. So S1 D1 equal S2 D2. This is the motor and as the driver machine, and this is the driven machine. Could be blower, it could be pump. This is belt problems, start as subsynchronous vibration. Belt problems all start as subsynchronous vibration. For looseness, you'll have the rotating looseness will be 1x and harmonics, and this will be indication of rotating looseness if your bearing is loose inside the housing. Of course, not that much. So if the bearing is loose inside the housing, this will cause high 1x vibration with harmonics. If you have structure looseness, as we mentioned in the first fault analysis, it will show high 1x vibration in the radial direction, because the radial direction is the direction with the less stiffness and higher flexibility than the vertical. So you'll see high 1x vibration on the horizontal direction, and the levels of the vibration between horizontal and vertical will be significantly different. And reason for that is the significant difference on the stiffness between horizontal and vertical. As you can see here, this is also some sort of the looseness. You will see if you have looseness in the hold down bolts, this is also can cause high 1x vibration. And you will see phase difference about 180 between the base of the motor or the motor itself and the base. For structural looseness, as you can see here, this motor is, this gearbox is built driven by the motor. And also, as you can see here, it's fixed from this structure, so you can have structure looseness. This motor is hanged to the gearbox, you will have structure looseness. This vertical motor as well, you'll have high vibration on the non-drive end. So this is all examples of how the structural looseness will look like. Like as you can see here, this motor is just over this bracket, and with the motor weight and the assembly and the design, even you see they put this bracket here just to give some support, but it doesn't help that much. So all these examples and all these machines have structural looseness problem. the mechanical looseness will cause 1x and harmonics. If you have cooling fan cover loose, can cause mechanical looseness and 1x with harmonics. This is 1x with harmonics, indication of looseness, 1x with harmonics, all this indication of looseness problem, 1x and harmonics, looseness. The next fault we're going to talk about is the electric motor faults. If you have a stator eccentricity, you will see the twice line frequency, which is 100 hertz or 120 hertz. And this will be indication of soft foot problem. You have a casing distortion, you have uneven air gap variation between the rotor and the stator will cause high 2x vibration. If you have rotor eccentricity, you will see the twice line frequency modulated with sideband at PPF or the ball bus frequency. The ball bus frequency equal the slip frequency multiplied by the number of balls. The slip frequency is the synchronous frequency minus the rated frequency or the rated running speed, and synchronous frequency equal twice line frequency divided by the number of balls. And when you calculate the ball bus frequency, and if it is as a sideband around the twice line frequency, this will be indication of rotor eccentricity. This is stator eccentricity here. As you can see, in the stator eccentricity, you will see difference between the air gap at the vertical and horizontal direction. But the stator is fixed, it's not moving. But with the rotor eccentricity, the rotor is dynamically moving inside the rotor, and this is what we call rotor eccentricity. With this one, you will see only 2x, sorry, only the twice line frequency, but with this one, you will see the twice line frequency modulated with side bands at the pole pass frequency. And this is in case you have soft foot, like when you shim here, you will still have soft foot. So when you tight the bolts, and this one get tightened, you will have casing distortion, and this would cause stator eccentricity. Rotor bow, similar to what cause high 1x vibration. We spoke about this one. You will see the high 1x vibration on the axial direction. If you have loose in the winding, this will create twice line frequency with harmonics. Like you'll see twice line frequency, which is the one with harmonics, and this will be an indication of loose in the winding. If you have cracked or broken rotor bar, you will see the running speed of the motor with harmonics, which is similar to looseness. However, this will be modulated with sideband at the pole pass frequency, which is the slip frequency multiplied by the number of poles. For the loose rotor bar, you will see the twice line frequency, and you'll see the rotor bar passing frequency, which is the number of rotor bars of the motor, with sideband at the twice line frequency. This will be indication of the loose in rotor bar. If you have silicon control rectifier or SCR, you will see 6 times the line frequency in your vibration spectrum. And if you have rotor operating of magnetic center, you will see natural frequency on the axial direction. This twice line frequency, this is a case study, and this was, you see the twice line frequency was low and start to increase over time, and then suddenly increase to be about 6 millimeter per second, and this is what we have. We have short in the windings of the stator, or have short in the stator here. If you have broken rotor bar, you will see the running speed with harmonics modulated with sideband at the pole pass frequency. This is the rotor bar with sideband at twice line frequency, and this will be indication of loose rotor bar. For gearbox analysis, the first fault we have is the gear tooth wear. Like you can see the shaft speed sideband around the gear meshing frequency. You'll see gear meshing frequency, the second and the third. And as you can see here, this is an indication of gear tooth wear. And the vibration will be higher at the gear meshing frequency and the third harmonic of the gear meshing frequency. With misaligned gear, you will see the gear meshing frequency with highest vibration at the second gear meshing frequency. So with the tooth wear, you will see the first and third. With the misaligned gear, you'll see higher vibration in the second gear meshing frequency. And the gear meshing frequency is the number of tooth of the gear multiplied by the running speed for sure. We have the hunting tooth, and the hunting tooth is like one tooth of the gear, trying to hunt the other tooth of the other gear, and this will increase the frequency of matching between these two, or meshing between these two tooth, and this will increase the wear rate, and it will be seen as subsynchronous frequency, and the hunting tooth will be equal the gear meshing frequency multiplied by the product of the gear of the two gears in the gearbox multiplied by the number of teeth of the first gear and the second teeth and number of teeth of the second gear, and the product will be the common factor product, and there is a way to calculate this common factor, and the result of this one will be very helpful to calculate the hunting tooth. Cracked or broken teeth, you will see impact on the time waveform. The time waveform is essential on the analysis of the gearboxes. And when you see impacts on the time waveform, this will be a very good indication of cracked or broken teeth. You can see here in this gearbox, like S1, Z1 equal S2, Z2, which is the running speed of the first gear, multiplied by the number of teeth of the first gear, equal the number of teeth of the second gear, multiplied by the number of teeth of the second one, and so on. And the gear meshing frequency will be S1, Z1, or the number of teeth of the first gear multiplied by its running speed. Oil analysis is very, very important in gearbox analysis. This is cement mill girth gear, which is a bit more complex. This is a mill gearbox, as you can see, the input speed, and this is the two different stages. And this is a good one to calculate this information. It's better to mention this way. Like, let's see here, this is Z1, which is 17. Z2 here is 24, and Z3 is 15. So the input speed was 24.6 hertz. The gear meshing frequency 1 equal the 17 multiplied by running speed. So you get the gear meshing frequency, which is for these two gears, as Z1 S1 equal Z2 S2. So 17 multiplied by 24.6 equal the Z2, which is 24 multiplied by S2. Then I calculate the speed of the S2, or the second shaft speed. The gear meshing frequency 2 for this shaft equal, here as you can see, 17.4, which is the speed, multiplied by the 15, which is the number of gears for this one. So we can say that these two gears have same gear meshing frequency as long as they meshing together. But we cannot say that this gear have the same like this one, because it's not meshing with this. But this gear meshing frequency between the Z3 and Z4 gears, yes, it will be equal, because the two gears are meshing together. Don't get confused about that. And S2 Z3 equal Z4 S3. So we have the S2 is 17.425 multiplied by 15, which is this one, equal the S2, which is the running speed of this second or the third shaft, multiplied by the S3. And we got the S3, which is the speed of this shaft is, the S2 is calculated here. And we have, 52, which is the number of teeth here, multiplied by the S3. So we got the S3, which is the speed of this shaft, which is 5.026 hertz. The third gear mesh will be 5.026 multiplied by 15, which is this gear. It will be 75.39 hertz. Then we have the S3 multiplied by Z5 equal S4, which is the last shaft, multiplied by Z6. S3 is 5.026 multiplied by Z5, which is 15, that one, equal 48, which is the number of teeth for the big gear, multiplied by S4. So the last output shaft was running with 1.57 hertz. This is the speed of the last shaft. For gears Z5 and Z6, like this one and this one, we have this one 48 teeth, which is equal to by 2 by 2 by 2 by 3 by 1. And this one, which is 15, equal 3 multiplied by 5 multiplied by 1. So what is that? This is what we call the common factor. This is how we calculate the common factor between two gears. So what is the common factor here? 3 and 1 and 3 and 1. So the product of the common factor will be, this is the 3. So the product of common factor will be 3 by 1, which is 3. So if we calculate what we call the gear assembly phase factor, it will equal the gear meshing frequency multiplied by the product of the common factor. which is the gear meshing frequency between these two is 75 divided by the common factor. You calculate this one. And if you want to calculate the hunting tooth, will be the gear meshing frequency, which is 75.39 multiplied by the product of the common factor, which is 3, divided by Z5, which is 48, multiplied by 15, which is 0.314 as sub-synchronous peak. So here with this example, we would be able to calculate the speeds, the gear meshing frequency, the common factor, the product of the common factor, the gear assembly phase factor, and the hunting tooth frequency. As you can see here, this is your vibration spectrum showing the running speed with many harmonics. And if you didn't see the time waveform, you will never know that you have a broken tooth. But when we look to the time waveform, you see high amplitude repeated impacts as indication of broken tooth. And when we do endoscope to check here, or sorry, borescope to see here, you will see a broken tooth here as a result of that we see this peaks here on the, or sorry, this impact here on the time waveform. And this is the circular plot, which showing also high amplitude impacts as a result of broken tooth. Also, you can see as a worn gear, you will see the gear meshing frequency with side bands at the running speed. And this is the gear meshing frequency with side bands. And you'll see amplitude modulation over time waveform. This is the gear meshing frequency with side bands. Gear meshing frequency with side bands, the second harmonic. And this is all indication of the fault. Yep. And that's it. Let's have a look on the question. If we have two fault conditions having similar spectrum, do we have carry out further analysis to pinpoint the fault, and what are the analysis technique we can use? For which fault you're talking about, Martins? If you have two fault conditions having similar vibration spectrum, like you mean you have unbalance and another thing have similar FFT, like unbalance and misalignment, and they have similar spectrum, is that what you mean? Unbalance and structure looseness. Okay, if you have unbalance and structure looseness and they have similar spectrum, how you can know the difference between them? This is your question. Very good. If you have unbalance, normally with unbalance, as unbalance is a centrifugal radial force, you will see high vibration at both horizontal and the vertical direction. And because the horizontal direction has less stiffness, so the effect of unbalance in the horizontal direction will be higher. That's why we'll see higher vibration in the horizontal direction than the vertical direction. But the difference between them in the amplitude will be twice to maximum triple the difference. And because of that, you can say we have unbalance problem. But with structure looseness, the vibration in horizontal direction will be way higher than the vertical direction. And also, as Ahmed said, we can use the phase analysis, and time waveform will be very similar, but the phase analysis will be more effective. Because as long as you have 1x vibration on the spectrum, you will see sinusoidal time waveform. But you need to look for the amplitude, and also you need to look for the phase measurement. That should be your solution to know the difference between them. So if you get confused, more investigations need to be done. C3X in radial direction, bump non-drive end side. It could be for many reasons. It could be misalignment. This could be one of the reasons. I don't know how many, like it could be as we mentioned, if you have a certain coupling types, it can excite certain frequencies in your vibration spectrum. So if you have coupling misalignment, can cause that. In some situation, if you have casing distortion or pipe strain, also can do that, can increase the 3x vibration in the bumps. I'm not sure if this bump, it could be weir rings. That could be the reason. Weir rings also can cause something like that. And there is many situation can cause uh, increase the 3x vibration. We need to see if the how the bump looks like, how the bearing looks like. Is the bump is in center hung between the two bearings, or you have the bump as overhung? All these things can affect the vibration pattern and the answer. Yep. For bearing fault, why is stage 1 frequency usually higher than stage 4? Any explanation for this? Why stage 1 frequency higher than stage 4? You mean why we see high vibration in the high frequency range, not the low frequency range in stage 1? Is that your question? Good. Because the high frequency, it will be easy excited by any frequency generated by the bearing. You have your bearing, and the bearing faults is a frequency with very low amplitude and a very high frequency. And that's why we use what we call HFD, or high frequency detection techniques. You have a very quick event, you have a very high frequency event happen with very low vibration. Normally the high range is excited by any frequency, the high range vibration. Because if you look for the linear range of your accelerometer, you will see that above a certain frequency range, like 2 or 3,000, the vibration will be magnified automatically because of the linear range of the accelerometer itself. And if you have any small amount of vibration happen with very high frequency, it will be excited at this range. That's why it will appear with higher amplitude at the higher frequency, because it is an event with very small amplitude and very high frequency. Once this event starts to develop, the frequency of the event you are getting, it will excite the lower frequencies, and it will appear easily at the lower frequency range. Like normally the bearing fault frequency is the same. Like for example, if you say the outer race is 75 hertz, so this is the same frequency. But if you have friction, if you have some noise, if you have lack of lubrication, if you have metal to metal contact, all of these faults or events happen with very high frequency and very low amplitude. That's why we mostly see them on the high frequency range. How can we reduce piping vibration? This is a very generic question. This can be done by doing ODS or model analysis or motion amplification, and you see if you need to add some stiffened supports, some points or some location, and that will be very helpful to reduce the piping vibration. Many reasons, even the process. Can you give valuable words on model analysis? Model analysis, I'm going to talk about it in another session, and it's very important technique, can be used to detect the natural frequency and the mood shapes of the structure and the machine, and it have to be done while the machine is not running. It's very effective to detect the natural frequency, the mood shape, doing some modification for the structure to shift the natural frequency and avoid being in a resonance. If there is any course on the piping vibration, I'm not sure. I'm not aware of that. It could be, but I never heard that never heard about it. Like there is a certain vibration analysis course just talking about the piping vibration analysis. Okay, that's it. Thank you so much, everyone, for attending, and very happy that you joined me in this session. I will upload the session to the YouTube so everyone else can see it, and looking to see you next month on the next session. Enjoy the rest of your day, and thanks all, and Assalamu alaikum for those who speak Arabic. Thank you so much, Martin, and see you next time. Bye for now. Thanks عمرو. شكرا. ربنا يتقبل منا ومنك يا رب. Thank you very much, everyone. Thanks.